Okay, hopefully we have some coffee brewing and our popcorn popped. We're going to go back and review some relationships that we dealt with during the first part of this quarter. In this next section, we're going to look at concentrations and try and understand that relationship and apply it to a variety of different problems. Remember, there's a lot of different concentrations and the units that go with them. The one that chemists use a lot, a majority of the time, in a lot of different situations, is molarity. And the units for molarity it's an abbreviation of units. It's like saying density. What's the units of density? Molarity is how many moles of a solute per liter of solution. So we've had a lot of dropper bottles labeled in laboratory with molarity. We haven't really worked with it that much, but a dropper bottle that's labeled 6M HCl. So the M is an abbreviation. I mean, the M means molarity, but it means there's 6 moles of HCl for every liter of solution. In that form, it's written as a conversion factor, as a relationship, 6 moles of HCl for 1 liter of solution. So let's look at an example problem. Say we're making a solution, and in the laboratory we measured out 2.5 grams of sodium chloride, and we put it into a graduated cylinder, and we added enough water to make a 50 milliliter solution. In this problem, what is the molarity? So the concentration is 2.5 grams of sodium chloride for every 50 milliliters of solution. That's a concentration unit. It's a perfectly acceptable one. But what if we wanted to have it in units of molarity? So we want to eventually get the units to be moles of sodium chloride per liter of solution. So how do we do that? Well, you need to get the gram portion, convert that to moles of sodium chloride. And I think all of us could do that, knowing the molar mass of sodium chloride. And then separately, use a conversion factor or two to get milliliters of solution into liters of solution. So go ahead and pause the video and convert that concentration into moles per liter. The first conversion factor will convert milliliters into liters. So milliliters and milliliters cancels, and then we have the bottom part in per liter. And the second conversion factor, the molar mass of sodium chloride, grams and grams cancels, and we're left with moles of sodium chloride per liter of solution. And when we do the math, our answer is 0.85 moles of sodium chloride per liter of solution. Note, you can leave your answer like that, but we also need to be aware that you can use the big M to represent moles per liter. So if you wanted to, and often problems are given that way, you could have written it like this: 0.85 capital M, which means molarity, NaCl. And again, big M is an abbreviation for units. It means moles per liter. And also note, when we do label concentrations, we always you make the concentration and its units, but you also have to label what's the solute that's mixed in there. So there's the molarity of this solution. In this next example problem, you're going to use concentration again, but it's a little bit different type. In this example problem, you want to make a solution to a certain concentration. You want it to be 0.2 molarity. You're going to make it in a container, and the total volume of the solution is 250 milliliters. You're going to make it in something called a volumetric flask. And this is actually something you're going to do in the laboratory. Volumetric flasks are very similar to graduated cylinders, except there's one marking on there to that volume. So here's an example of a volumetric flask and what it looks like. You put your solute in there, and then you add enough solvent till you go to that one marking. So unlike a graduated cylinder that has many markings, this just has one. And in this particular one, it has a marking for 250 milliliters. So you know the volume of your solution, you know what concentration you want to go to. The question is, how much of that salt do you need to put in there to make that concentration? So how much could be a little relative, but in the laboratory, what unit should we go to? What would we have in our typical laboratory? We have balances that can give us grams. So we're going to figure out how many grams of copper sulfate salt do we need to add to make that particular concentration in that volume. So in our problem, we have two different measurements. We have the 250 milliliter flask and the 0.2 molarity solution. Which one do we begin with? Well, like all stoichiometry problems, the unit we're going to has one unit. So the beginning number, the measurement we're going to use, is the 250 milliliters, the 0.25 liter flask. The concentration we're going to use as a conversion factor. So let's write that concentration as a relationship. So pause the video, and instead of having it big M, write that with its units and be as anal as possible. So pause the video, unpause when you have the relationship. So that concentration relationship says if you're going to make a liter of the solution, you need to add 0.2 moles of that salt. Since we're only making 250 milliliters, whenever we get to the mole amount we need to add, it should be less than 0.2 moles. The concentration relationship gives us a ratio between liters and moles. So we're starting with liters. We could use this as a relationship to make a conversion factor. After we use that, that would tell us how many moles of the copper sulfate salt that we need to add. So how do we get to grams? Once we have moles of that salt, then we could use the molar mass of that salt and get it into grams. So before we do the molar mass as a conversion factor, we need the molar mass. So pause the video, and somewhere on your page, write the molar mass of the copper sulfate pentahydrate salt. And yes, you have to include the 5 waters in your molar mass, because when you measure that out on the scale, you're measuring those 5 waters. You need to get the molar mass of the copper sulfate plus 5 water molecules for your total molar mass. So go ahead and pause the video, unpause once you get that relationship. 1 mole of copper sulfate pentahydrate is approximately 250 grams. So there's the molar mass. Now we can do our conversions. Go from liters to moles, and then moles to grams using that conversion factor. So pause the video, get an answer, and let's see if it's reasonable. And by the way, there's the answer right there. You should be getting something really close to 12.4. So pause the video, see what answer you get. After making sure our units all cancel, liters and liters of solution cancels, moles of the copper sulfate salt and moles of the copper sulfate salt cancel, and we're left with grams. When you get your answer on the calculator, it's approximately 12.482 grams of copper sulfate pentahydrate. When you do this type of work in the laboratory, what you're going to be doing in upcoming labs, you would measure your salt on a balance using some sort of measuring cup or measuring paper, and then you would carefully try and get all of the salt into the volumetric flask. It's a pretty small opening, so it may be a little difficult. And if you spilled anything, you know what you do? You start over. But regardless, get all the salt into the volumetric flask, and then you add enough water to fill it to the marking, and usually that marking on the volumetric flask is somewhere along the neck in this area. You do have to be a little bit careful in the end. When things dissolve and mix, it's kind of funny. Sometimes when you add a salt to water, the volume gets bigger, sometimes it gets smaller. So typically try and get all of the salt dissolved, and then in the very end, using a pipetter of some sort, put enough liquid, drop by drop until you get to the marking. If you go past the marking, what would you do? Yeah, you wouldn't stick something down in there and suck up any liquid, because you'd suck down some of the solute too and not have the correct concentration. Yeah, you would start over. On this slide, we have even more practice problems. And you may ask, why do we keep doing practice problems on concentration? Practice problems are there to try and reinforce what you've learned. They're also there to teach you. This first problem we see looks very similar to the first two we did, but it's slightly different. So in this one, like the previous one, you want to make a solution with a certain concentration. On the previous example, you knew what volume you wanted to go to. In this one, you know how much solute. And in this problem, you're trying to determine what volume you should add. So what should the volume of your solution be if you wanted this particular concentration, and this is how much solute you have? Volume could be any unit, but since we have molarity and we know that's a ratio of liters, we're going to go all the way to liters of solution. If you wanted to go to gallons and get an answer, that's perfectly fine. If I'm not specific on the unit of volume, you can go to any type. But this is the answer I'm going to. So we're going to something with 1 unit, so we're going to start with something with 1 unit. So we'll start with 0.949 grams of sulfuric acid. Molarity is a relationship between moles and liters. To get to liters, using moles to liters, what would we do? Well, a logical step would be to convert that gram amount of sulfuric acid into moles, and then you could use the concentration relationship. Go ahead and pause the video. This is going to take 2 conversion factors at least, and convert grams of sulfuric acid into liters of solution. Unpause when you're ready to see the answer. Keeping track of and understanding when to use different relationships in a unit conversion problem is the hardest part. But regardless, we should always cancel our units when we're done to let us know that we've done things correctly. Grams of sulfuric acid cancels with grams of sulfuric acid. Moles of sulfuric acid cancels with moles of sulfuric acid. And we're left with liters of solution. And our math, when we're finished, is approximately 0.0450. So if you added 0.949 grams of sulfuric acid, add enough solvent to make a 45 milliliter solution, the molarity would be 0.215 moles of sulfuric acid per liter of solution. The next type of problem is a little different than the previous ones we've just done. In this one, you're given the percent by mass of ethanol in an aqueous solution. And all you have to do in this one is convert that concentration unit into molarity. It's going from one concentration unit to another. It's the same concentration, but different units, so we're going to have different numbers. Density, for some reason, is given. That's the density of the solution. And yes, you're going to use it in the problem. Hopefully it becomes clear as you try and convert units. Before you start, I want you to write the percent by mass in terms of its units. I mean, percent W over W is not a unit. So write that 40% by mass in terms of units, and then before we start, write the units of molarity. What units are you going from, and which ones are you trying to go to? So pause the video, unpause when you're certain you have the right ratios. 40% W over W. Remember, W means grams, so it's grams over grams. 40%, that's 40 out of 100. So 40% W over W ethanol, there'll be 40 grams of ethanol for every 100 grams of solution. Molarity, how many moles of ethanol per liter of solution? So what are we doing? What are our conversions? You need to convert grams of ethanol into moles of ethanol. That's not hard. I think we could use molar mass. The other one, you need to convert grams of solution into liters of solution. It's grams of something to liters of the same thing. Grams the volume, grams the volume. What gives you the relationship between grams of something and volume of the same thing? That's density. So you're given density of the solution, and you'll be using that in a relationship to convert grams of solution to liters of solution. It may take more than one on the relationship to convert the bottom one, but it's going to take at least that density one. So go ahead and pause the video and see what answer you get. In the first conversion factor, the molar mass of ethanol was used, and grams of ethanol and grams of ethanol cancels. And after the first step, the concentration, the units would be moles of ethanol per 100 grams of solution. The next few steps, we're going to convert the grams of solution into liters of solution. The next conversion factor we're going to make is using density. And what does that density tell us? It's the density of the solution. And it says if you had a milliliter of solution, there's 0.93148 grams of solution. But as far as just our unit conversion, grams of solution cancels with grams of solution. We eventually want to get to liters of solution, so that's the next conversion factor. And milliliters of solution cancels with milliliters of solution. And when we do our calculation with our numbers, it's approximately 8.088. For every 1 liter of solution, there's 8.088 moles of ethanol. That's the exact same concentration as 40 grams of ethanol per 100 grams of solution. Get different numbers with different units. On this page is an example problem of stoichiometry using concentration. Go ahead and pause the video and figure out what's your A, what's your B, what unit are you starting with, and what unit are you going to. Again, you can use this stoichiometry outline in your information packet as a guide. So go ahead and pause the video, unpause when you've figured out your A and your B, and kind of your outline for your conversion factors. As always in a stoichiometry problem, the one you're given information about is your A. So the KOH, that quantity, that's our A. In the problem, it wants to know how much water would be formed. So water is our B. So in this problem, we're going to start out with our A, 25 milliliters of KOH. If you can get that into liters, then you can use concentration to figure out how many moles of KOH have been added. Using the chemical reaction, you can then figure out how many moles of water are being produced. And using the molar mass of water, our B, we can figure out how many grams of water is being produced. So go ahead and pause the video and go ahead and set up the stoichiometry problem. Unpause when you have an answer. So shown here are the 4 conversion factors to get the amount of water that would be formed if 25 milliliters of the 6 molarity KOH solution reacted with excess phosphoric acid. The answer is approximately 2.70 grams of water would be formed with that 25 milliliter solution. We often take solutions, add more solvent to dilute them. Shown below is an equation that can be used to calculate what the new concentration is if it was diluted. It's C1V1 equals C2V2. Conditions are labeled 1 and 2, but it's not specific on which one has to be 1, but 1 could be the higher concentration and 2 could be the lower concentration. C1, if that's the case, would be the higher concentration. C2 would be the diluted concentration. When you use this equation, it doesn't matter what the concentration unit is. It could be molarity, it could be percent by volume. As long as the concentrations have the same units, you can use any unit you want. V1 and V2, V1 would be what volume of the concentrated solution are you using? V2 is the total diluted volume. It's not how much solvent you add. V2 is the total diluted volume. The volume units for this equation, again, it doesn't matter what volume units you use. Could be milliliters, could be liters, could be gallons. But if you're using one particular volume unit on one side, it needs to be the same volume unit on the other side. So let's see an example problem. When we buy solutions, especially acids, we usually buy them at a concentrated concentration. It's a lot cheaper to send chemicals concentrated than to send them at the concentrations you need to use. HCl that we buy commercially is always 12.4 molarity. In the lab, we've used dropper bottles where the concentration was diluted to 6 molarity. The dropper bottle volumes were 50 milliliters. The question here wants to know how much of the 12.4 molarity solution do we need to use, and then add enough solvent to make a 50 milliliter solution. So we're given the concentrated solution, the concentration, we're given C1, we know what concentration we want to go to, we know the total volume, V2. What we're trying to figure out is what's the how much volume of that concentrated solution do we need to use? Make sure your answer makes sense. It should be less than 50 milliliters. Go ahead and pause the video, use our dilution equation, and see what answer you should get. After plugging in the numbers in the equation, rearranging, we have our math equation, and we need to cancel units just like any other type of problem. Molarity of HCl cancels with molarity of HCl, and we're left with milliliters. The answer is approximately 24 milliliters, 24.2 milliliters. That answer makes sense. I mean, the initial volume should be less than the total diluted volume. In this next section, we're going to look at quantitative analysis. When you do quantitative analysis, you're trying to figure out how much of some unknown is in something else. You're doing measurements. A good example, if you had an ore and it was a rock and you want to know how much of some sort of metal was in there, like gold. Or if you're looking at your blood and you want to know how much of glucose is in your blood. You're trying to figure out how much of something is in something else. If you were a pharmaceutical company and you made a drug and you really believe that there's a certain amount of that active drug in that drug, you could perform quantitative analysis to figure out exactly how much of that drug is in that pill. For those of you that have quantitative analysis, analytical chemistry in your horizon for your particular degree, this is a pretty important chapter. On this page, I'm going to describe a quantitative analysis study for an upcoming laboratory that we're going to do. And in this upcoming laboratory, we're going to have vinegar. Vinegar is a very complex mixture, water-based, lots of different solutes in there made by the organism that produced it. but the chemical we're looking for is acetic acid. We want to know what's the concentration of acetic acid in the vinegar. Shown here is the setup of our experiment that we're going to conduct in the laboratory. We're going to put the vinegar into a beaker. When we do this, we're going to put a very specific volume of vinegar in there. Eventually, we want to get the concentration. So we know how much volume's in there. If we could just figure out the quantity of acetic acid in that volume, we're good to go. When we do it in the laboratory, we're going to put exactly 10 milliliters of vinegar into that burette. So if we're going to do concentration, if we knew how many moles of acetic acid were there in that 10 milliliters, we could get concentration. Concentration is how much solute per solution. We know the 10 milliliters. Our only question experimentally is how many moles are in there. So what else is here? Also part of the experimental design is something that's called a burette. And a burette is a volumetric device just like a graduated cylinder. It has a valve that allows you to add liquid. In this burette, we're going to be putting a liquid. And we're going to be putting in a solution that has a chemical that is very, very specific with acetic acid, meaning it only reacts with acetic acid and none of the other components that's in the vinegar. So what would that be? Well, acetic acid, it's an acid, so what would we put in there? We're going to put a base. Acetic acid is the only acid component, virtually the only acid component of any concentration that's in vinegar. So we're going to be putting a base in there. In our experiment, the base that we're going to be putting in there is KOH, and it's going to be an aqueous solution. So we're going to do a neutralization reaction when we add the KOH to the vinegar. How does that give us the moles of acetic acid? I mean, all we're doing is a reaction, and we can't really see the reaction. We can't see the products that are being produced. You're also going to add another chemical. You're going to add an indicator that's called phenolphthalein to the vinegar solution. There's lots of different indicators that exist, and it depends upon what chemical you're looking for. But this indicator, this phenolphthalein, as long as there's any acetic acid molecules in the vinegar, it stays colorless. As soon as every acetic acid molecule is neutralized, it turns pink. So less than a half a drop, this solution will turn pink and it'll stay pink. This is our visual clue. We're using our eyes for this experiment. This is our visual clue that we've added just enough base to neutralize all the acid. We call this the endpoint of this quantitative analysis. In this particular quantitative analysis, our endpoint, when we're done with it, is when we've added enough KOH to neutralize all the acid in vinegar. So how's that giving us the moles of acetic acid? Well, there's another piece of information that's also given to you. The concentration of what's in the burette has to be known. So, all this information, somehow we're going to get moles of acetic acid. So what do we have so far? We know what volume of KOH was added to reach the endpoint. We know its concentration. If you know the volume and the concentration, you could figure out how many moles of KOH were added. You also need to know the chemical reaction. The chemical reaction, that mole-to-mole ratio, if we had that, which you would for any of these quantitative analysis studies, if you have that chemical reaction, if you know how many moles of A of that KOH were added, the mole-to-mole will tell you how many moles of this acetic acid were neutralized. This is, maybe you're figuring it out, this is a stoichiometry problem. There's an A and there's a B. The A, like every other type, is what's known. We know how much KOH was added. We know its concentration. The B, how much, where's the question mark? The B is how many moles of acetic acid were in there. So if we kind of look at this stoichiometry problem, the volume of the KOH, this again, this is our A, KOH is our A. The volume of the KOH, we could convert that into moles of KOH that were added using the concentration of the KOH, which we would have. That would tell us how many moles of the A reacted. Using the chemical reaction, we could figure out how many moles of acetic acid were neutralized. That's how many moles were in the 10 milliliters. We could plug that in and get the concentration of acetic acid in vinegar. So this quantitative analysis, you have to have some knowns. You choose a reaction that's very, very specific between your A and your B. If there were other acids in vinegar, then the KOH wouldn't be specific to acetic acid. You'd be getting the concentration of all the acids that are in vinegar. So you have to pick a chemical reaction, and you have to pick an A that only reacts with your B, your unknown. Okay, let's go ahead and use this concept that we just taught and apply it to a different reaction. It's also an acid-base reaction, but we'll apply it to that. Later on, we're going to look at other quantitative analysis experiments, but instead of being liquids, we're going to be looking at solids. So there's lots of different ways we can apply this, but the heart of it, they're all stoichiometry problems. And one last definition to give for this slide. This type of quantitative analysis that was just described is called titration. When we use a solution, a volume of solution, from the known, from the A, when enough of that is added until the reaction is just complete. There's other types of quantitative analysis that we'll talk about later, but this particular type of quantitative analysis is called titration. On the next few slides, we're going to do quantitative analysis problems. And in these problems, we're going to try and figure out how much sulfuric acid is in a 50 milliliter solution. When we do this, we're going to be putting the 50 milliliters into an Erlenmeyer flask. So in that flask is 50 milliliters. A goal of the experiment would be to figure out how many moles of sulfuric acid is in that 50 milliliters. Using that mole quantity, we could figure out the concentration of sulfuric acid. In the burette is a 5.4 molarity KOH solution. In this titration reaction, in this neutralization reaction that we're doing, the aqueous solution of potassium hydroxide would react with the aqueous solution of sulfuric acid. It's an acid-base neutralization reaction that's going to form water. So here's our chemical reaction that's part of the titration reaction. Remember, this type of reaction would be given for any titration reaction. Also remember that sulfuric acid is a diprotic acid, so that's why there's two potassium hydroxides. To the sulfuric acid solution, phenolphthalein is added. And phenolphthalein isn't specific to acetic acid, it's specific to acids in general. If there's acid that are in the solution, if the solution's acidic enough, the phenolphthalein molecule is colorless. Once all the acid molecules are neutralized, it turns pink. So the phenolphthalein was added to the Erlenmeyer flask. When you do this in the laboratory, you only need a couple drops, so not very much. So a couple drops of phenolphthalein would be in there. 50 milliliters of sulfuric acid would be in the Erlenmeyer flask. Once you have that in there, you'll start adding your base, the potassium hydroxide. This is our A. The sulfuric acid is our B. As you add the potassium hydroxide, so you use the valve to open and close. But as you add it, you'll grab onto the Erlenmeyer flask and swirl it to mix it. At some point, you'll be adding the potassium hydroxide slowly. The solution is going to turn pink and remain pink. And that's what we call our equivalence point, the end point. This end point is when you've added enough of the A to completely react with all the B. And for this neutralization reaction, this is when you've added enough of the base to neutralize all the acid. Once the sulfuric acid is gone, the solution turns pink and remains pink. When you reach the end point, using your values from the burette, you can calculate how much KOH solution, or whatever your B solution is, how much of that was added. Let's give some hypothetical data. Let's say that it took 75 milliliters of the KOH solution to neutralize all the sulfuric acid that was in that 50 milliliters of sulfuric acid. With that information, with the volume of KOH that was added, using its concentration, and using the chemical reaction, we can use those three pieces of information to calculate how many moles of sulfuric acid were neutralized. So let's write down the information we're going to use for the next page. So this hypothetical 75 milliliters is something that you're going to be calculating experimentally in class for different solutions. So we'll use that starting value for our quantitative analysis problem solving on the next page. So in this first problem, this first quantitative analysis problem on this page, the question wants to know how many moles of sulfuric acid were in that 50 milliliters of solution. So not concentration, but how many moles were in there. So we know from the previous page in its data, it took 75 milliliters of the KOH solution to neutralize all the sulfuric acid. That's given within the problem. Also given from the previous page is the concentration of the KOH solution. So knowing the volume of KOH that was added, its concentration, those two values, those two measurements will allow us to calculate how many moles of KOH were added. Using the chemical reaction gives us a mole-to-mole relationship. Knowing how many moles of KOH were added, we could calculate how many moles of sulfuric acid were neutralized. So go ahead and pause the video. Starting with this 75 milliliters, eventually calculate how many moles of sulfuric acid were neutralized. So this outline of converting units, this stoichiometry problem, we can also see this general outline in our information packet. Our A is the KOH, and we're given the volume amount, and that KOH is part of a mixture. Always in any stoichiometry problem is to get to moles of A. This M is the concentration in molarity. So we started with milliliters, need to get that to liters, then using the molarity proportion, we can get to moles of A. Using the chemical reaction, we can get to the moles of B. Our B in this example problem is sulfuric acid. So in our example problem, we went from milliliters of KOH, liters of KOH, moles of KOH using the concentration, moles of sulfuric acid using the chemical reaction that's shown on the previous page. The answer we get, how many moles of sulfuric acid was in the 50 milliliters? 0.203. In the next problem, the problem wants to know what's the concentration, and in particular, what's the molarity of the sulfuric acid. When we do this problem, we need to know how many moles, and we need to know the volume. Well, if we look back at the problem, when you do a stoichiometry problem, you put an exact amount of the unknown into your container. We put exactly 50 milliliters of sulfuric acid into the Erlenmeyer flask. That's important. That's our volume. that 50 milliliters, we already know the bottom part of our ratio. The bottom part is 0.050 liters of solution. Now we only need to know how many moles are in that 50 milliliters. Well, that's what we just did up above. There were 0.203 moles of sulfuric acid. So just plug that into there, and we can solve the concentration. So 0.203 moles of H2SO4. And when we do our math to get it out of fractional form, there's approximately 4.0 moles of H2SO4 per liter of solution. So this is an important concept. The titration data didn't directly give us the concentration, but it allowed us to determine experimentally the quantity of the unknown that was part of the mixture. The fact that we experimentally measured precisely how much of the mixture was put into the Erlenmeyer flask, the 50 milliliters, allowed us to get concentration. In a little bit, in some other example problems, instead of liquid solutions, we're going to be doing it to solids. But if we want to get concentration, we always have to know exactly how much of the unknown we're studying, whether it's volume amount or mass amount. Okay, the last problem, we actually have all of our information, but instead of mole quantity, the question wants to know how many grams are in that 50 milliliters. How many grams of sulfuric acid are in that 50 milliliters? So go ahead and pause the video and determine that mass quantity. Using this mole amount determined in the first problem, we'll start with it. Using the molar mass of sulfuric acid, we can calculate the gram amount of sulfuric acid in that 50 milliliters. And it's approximately 19.9 grams of sulfuric acid is dissolved in that 50 milliliters of solution. Note, you may have, why would we throw grams at you? You may just have a problem with all that data that was given on the previous page. And instead of asking in the first problem how many moles of sulfuric acid, it could just ask how many grams of sulfuric acid are in that 50 milliliters. So here's some more information you can calculate using that titration data. In this next example problem, somehow we were able to gather some stomach fluid, and we want to figure out what's the concentration of the stomach acid. The acid that's in the stomach is hydrochloric acid. In this test, we're going to test 100 milliliters of the stomach acid. So, to find out the concentration, if we have precisely 100 milliliters of the solution, for the concentration, we have the value for the denominator. We know the volume amount. And again, to get concentration, we need to precisely measure how much of the unknown we have. We have 100 milliliters or 0.100 liters of the HCl solution. The question from the quantitative analysis, how many moles of HCl are in that 100 milliliters? The HCl is our unknown. That's our B in the stoichiometry problem. We're doing a neutralization reaction, and in this chemical reaction, it's a base reacting with the acid. There's only one acid in your stomach acid, so the base, and the one that's used in this problem, the calcium hydroxide, is very specific for the HCl. Your stomach fluid has a lot of different components in it. We're picking a reaction that's specific with the component of interest. The calcium hydroxide solution is of a known concentration. It's 0.1 molarity. During the titration experiment, there was some indicator that was added to the HCl solution, and it took 25 milliliters of the base to reach the endpoint, to reach the equivalence point. That's when the solution turned pink. So it took 25 milliliters of the 0.1 molarity calcium hydroxide to reach the endpoint. we're going to start the stoichiometry problem with our A values, what we know. We know it took 25 milliliters, so we're going to start with the liter of A. Using the concentration, we can figure out how many moles of A were added, and our A is calcium hydroxide. Using the chemical reaction, we can calculate how many moles of B, how many moles of HCl were in that 100 milliliters. Go ahead and pause the video and do this two-step conversion. So, starting with the 25 milliliters, 0.025 liters of calcium hydroxide solution, its concentration is 0.1 moles per liter. After that step, that will tell us how many moles of calcium hydroxide it took to neutralize all the HCl. The mole-to-mole ratio, for every 1 mole of calcium hydroxide that was added, 2 moles of hydrochloric acid were neutralized. And after that step, that's the number of moles that were in the 100 milliliters. We can take that number, plug it into our concentration ratio, and determine the molarity of the HCl solution in the stomach acid. So 0.005 moles of HCl divided by 0.1 liters, the molarity is 0.050 moles of HCl per liter of solution. That's the concentration of the HCl in your stomach acid. Shown on this page is another acid-base titration problem. Go ahead and pause the video and give the problem a try. Unpause the video when you're ready to see the answer, or unpause it if you need guided help as you attempt the problem. In this problem, we're trying to ultimately determine the concentration of boric acid. So this is our B. B's down here. Exactly 25 milliliters of boric acid was put into a beaker or some container, so we know the volume amount, 0.025 liters, since we're going to calculate molarity. The question is, how many moles of boric acid are in that 25 milliliters? And we'll do our titration analysis, our quantitative determination to figure that out. In the problem, you see that the A is our sodium hydroxide, and its concentration is 1.96 molarity. And to reach the equivalence point to neutralize all the acid, it took 4.74 milliliters. So sodium hydroxide is our A. So we'll start with the volume of the acid, the volume of the A, the volume of what we know, use its concentration and determine how many moles of the base were added, and then use the chemical reaction, the mole-to-mole ratio, to figure out how many moles of the boric acid were neutralized. So, starting with our A volume, the 4.74 milliliters, using the concentration of the sodium hydroxide as a conversion factor to determine how many moles of sodium hydroxide were added, and the mole-to-mole ratio, for every 3 moles of sodium hydroxide that were added, 1 mole of boric acid was neutralized. This conversion tells us how many moles of boric acid were neutralized were in that 25 milliliters. And the answer is approximately 0.00310 moles of boric acid. We can take this number and plug it into our concentration and get into our concentration ratio and get concentration. And determining this ratio, the ratio tells us that there's 0.124 moles of boric acid for every liter of solution, and that's our concentration. Shown in this example problem is another titration reaction, another quantitative analysis determination. This one is very similar to some previous problems we've seen. However, what's different is the concentration is for a solid, not for a liquid mixture. The solid is an alloy, and this alloy contains different types of elements, one of them being iron. And the type of metals that are in this alloy are such that we could pick a chemical that only reacts with that iron, and the chemical that we chose was an acid, sulfuric acid. So it's very specific for iron. The other metals that are in there won't react. Since this isn't a liquid mixture, we're not going to do molarity. We're going to do a concentration, and the concentration we're going to go to is mass percent. When we do this concentration determination, it's very similar in the fact that the unknown, we choose an exact amount, but instead of a volume amount, we have a mass amount of the alloy. That number is going to be used in the concentration. So before we move on to the titration problem, go ahead and complete this equation for percent by mass down here. So when you do percent by mass, it's a ratio. So what are the units up top? What are the units on the bottom? It's multiplied by 100. But go ahead and pause the video and write what you need up here and what you need on the bottom to get us percent by mass. When you do percent by mass, it's W over W. And remember, W means grams, so it's grams over grams. And on the bottom is the grams of the mixture, and in this case it's alloy, so we have grams of alloy on the bottom. Up top is how many grams of the component of interest, and in this case it's iron. We already know the grams of alloy. We know exactly, we put it in a very specific amount, so we know that bottom part. For here, just like on the previous titration problems, we'll use a titration data to figure out how many grams of iron were present. Okay, so we've kind of set up the experimental design. You put a mass of this alloy into a beaker, and you added sulfuric acid. Problem, if you read it carefully, what's our A? I mean, definitely our B. Definitely our B is iron. What is our A? What information in the problem is given? What quantity do we know about? So pause the video, write down your A, and kind of make an outline of a stoichiometry problem, a titration problem. And, eventually we need to figure out how many grams of iron were in there, and that number should go into that percent by mass problem. And it should make sense. It should be less than 2.358. Can't have more iron than your original sample. So pause the video, make an outline of what you're going to start with, and unpause the video when you're ready to check your answer. So this reaction's a little different from an acid-base neutralization reaction. It's not. You should recognize it as being a redox reaction. And during this type of test, what was measured was how much hydrogen was produced. And there's different devices that can do it, but we'll just trust the numbers that were given to us. You are told how much hydrogen is produced. What you know about is your A. So our A is how much hydrogen is produced. So we know how many grams of hydrogen was produced. We could determine how many moles of A was produced. Using the chemical reaction, we can figure out how many moles of iron must have been oxidized. And then using its molar mass, we could determine how many grams of iron were oxidized. And that's how many grams were present in the alloy. So, starting with the grams of hydrogen produced, using its molar mass, that tells us how many moles of hydrogen were produced. Using the chemical reaction recipe, we can figure out how many moles of iron were oxidized. And then using its molar mass, that tells us how many grams of iron were oxidized. And that's how many grams of iron were in that alloy sample. Take that number and plug it into our percent iron by mass equation, and we can get the concentration of iron. The number makes sense. The grams of iron is less than the grams of alloy, so we probably did everything correctly. We did do everything correctly. So the percent by mass was approximately 50% iron by mass. You could have written it 49.75% W over W or 49.75% by mass iron. But there's our final answer. Shown on this page is another quantitative analysis problem. Go ahead and read the problem, pause the video, read the problem, and decide what you're trying to figure out and what's the question asking you for. There's an A and a B, so label those, and when you're finished doing that, unpause the video to make sure you're on the right track. Ultimately, when you're finished with this problem, you're trying to figure out the molarity of the sodium sulfate. So sodium sulfate is our B. If you look at the problem, exactly 25 milliliters of the sodium sulfate solution was used. So if we're going to get concentration, we need to know how many moles of sodium sulfate are in that 25 milliliters. So as far as concentration and the volume amount, we already know the denominator. The question is, how many moles of sodium sulfate are in there? Look for your A. That'll be your starting measurement. And then eventually, we need to figure out how many moles of sodium sulfate is present. So go ahead and pause the video and get the problem going. This particular problem, we're using a precipitation reaction, and in it you had two salt solutions that were mixed together. The precipitate that formed was barium sulfate, and how much was collected was 5.79 grams. This is our A. A is our barium sulfate. The 5.79 grams is going to be our starting quantity. So in your conversion problem, you're going to start from grams of barium sulfate and eventually get to moles of sodium sulfate. How many moles of sodium sulfate precipitated to form that much barium sulfate? So starting with 5.719 grams of precipitate, barium sulfate, using the molar mass of barium sulfate, that would tell us how many moles of barium sulfate were precipitated. Using the chemical reaction, the mole-to-mole ratio, we get how many moles of sodium sulfate were present, how many moles precipitated. So 0.0245 moles of sodium sulfate were present in the 25 milliliters. Plug that number into our concentration ratio and we can get molarity. And the molarity determined for this quantitative analysis problem is 0.980 moles of sodium sulfate per liter of solution. And as you can tell from all these example problems, there's a lot of different ways and different types of chemical reactions that can be applied to do quantitative analysis. But ultimately the goal is to figure out how much of an unknown is there. On the next page, we're going to do another practice problem that has a slightly different angle. And again, these practice problems are there to try and teach you, reinforce what you've learned, but also teach you new things as you're conducting the problems. So make sure you know how to do all of these example problems. You never know which hard one's going to show up on that exam. On this page is another titration quantitative analysis practice problem. It's a little different than the ones you've seen before, so it may seem incredibly hard. Well, it is incredibly hard, but it's hard when you don't know how to do it. So let's try and do it so that you're better prepared and understand all the different aspects to quantitative analysis. Read the problem, write down what you're ultimately trying to figure out, and then unpause the video. Ultimately, you're trying to figure out the percent iron in a rock sample. This rock sample is called an ore. Like all the other quantitative analysis problems where we're trying to get concentration, we know exactly how much of the mixture we have. This solid sample, we have exactly 3.3 grams. we know the bottom part of our concentration problem again. That's 3.3 grams. What we need to figure out from our data is how many grams of iron are in that ore. The answer, how much is in there, make sure it makes sense. It should be less than 3.33 grams. Okay, so in this example problem, it's a little different in the fact that you had this rock sample, we added sulfuric acid, and there was a chemical reaction that's not part of the titration data. Sulfuric acid was added to this rock, to this mixture. The acid was added, and the acid oxidized the iron that was in the ore. The iron, the elemental iron, was converted into iron 2 plus the cation. Adding the acid in the very beginning was just a preparation step. It's not getting us the ultimate answer of how many grams of iron that's in there. But adding the acid to the ore formed an aqueous solution of iron 2 plus cations and solvated sulfate ions. The iron 2 plus cations, the iron sulfate, that sample then went through a titration experiment. And the reaction that's shown here, this is the titration reaction of the iron sulfate. Potassium dichromate and a sulfuric acid solution were put in the burette, and during this titration reaction, and it's not a neutralization reaction, this is actually a redox reaction, it took 43.7 milliliters of that sample, of that 0.15 molarity potassium chromate solution, to reach the endpoint. If we look at what's our A and what's our B, the potassium dichromate, that's our A. The iron sulfate, that's our B. We know the concentration of the A, 0.15 molarity, and we know the volume. Those two pieces of data can allow us to calculate how many moles of potassium dichromate were added, and then using the chemical reaction, the mole-to-mole ratio, we can figure out how many moles of iron sulfate reacted. And one more step that kind of adds a secondary complexity to this problem, that B is iron sulfate. We ultimately want how many moles of just iron. So how do we go from iron sulfate to just iron? That's where we use this reaction, this preparation reaction. For every 1 mole of iron that was oxidized, 1 mole of iron sulfate was produced. So this one's a little more complex because we're using a mole-to-mole ratio from this primary reaction, and we're using a mole-to-mole ratio from this secondary one. But ultimately, we want to get grams of just iron, not iron sulfate. So we need to know that number because that's the number that should go into there. Go ahead and make kind of a flow chart of how you should start and how you should end, and then go ahead and do the conversion factor. Take a peek at my flow of conversions and then try it yourself. So when you begin this problem, you're going to start with the volume of the A, the liters of the potassium dichromate. You can use the concentration to determine how many moles of potassium dichromate were added. The mole-to-mole ratio from the chemical reaction between iron and potassium chromate, that can be used to go between those two. The mole-to-mole ratio between iron and iron sulfate down here can be used to go between iron sulfate and how many moles of iron came from the ore. And then lastly, you can use the molar mass to go from moles of iron to grams of iron. That's all the conversion factors. Again, setting up the problem is the hard thing, but go ahead and put those pieces together and see how many grams of iron you get, and hopefully you get something less than 3.3 grams. So, starting with the volume of potassium dichromate added and its concentration, we can get how many moles of potassium dichromate were added that were needed to neutralize all of the iron sulfate. And for every 1 mole of potassium dichromate that was added, 6 moles of iron sulfate were oxidized. For every 1 mole of iron sulfate that was oxidized, it came from 1 mole of iron from the ore. And using the molar mass of iron, we can calculate how many grams of iron were in the ore. So that number is approximately 2.196. And that answer makes sense, and hopefully we did it right, which we did. I always do things right. It was less than 3.33. And the answer we get approximately is 66%. The iron in that ore is 66% by mass.